So for us to be able to understand the function of main memory unit, so let's consider this following illustration. So assuming that, as we know that logical address is being produced by the CPU, assuming that, and this is a product of the load time address binding and the compile time address binding. So prior to the execution time address binding, when the program is in the queue stage, waiting for a reference address, so this process will be executed. Now, in order for the logical address can be converted into a physical address, which is the real address that the main memory can understand, the MMU, or the memory management unit, will convert those logical address into physical address. But the question there is how. Now, the logical address, assuming that I have a logical address of 346 and the main memory unit will produce a relocation registers. This relocation registers is the exact, approximately, and the exact memory address available in your main memory, and this will be added to your logical address in order to produce a physical address. Now suppose I have a logical address of 346 and relocation register of 14,000. Now my physical address now is 14,346, which is the exact location of my program in the main memory. So this is how your main memory works with, and this is how essential is your main memory work with, particularly in the conversion of logical address into the physical address. Okay, so prior to discussing linking, now as we know in the previous discussions that we have, that during the load time and compile time, it requires binding of modules and binding of libraries. Now this binding requires linking at all. So when we talk about linking is composed of two types. We have the static linking and the dynamic linking. Now we will discuss first on the static linking. The static linking is a means of which system libraries and programs codes combined by a loader into a binary program image. Meaning to say, the linker will combine or grab or have a copy of the libraries that you have and put that copy in your program together with your module and compile it in order to provide a binary image or an execution or executable file. So if we're going to analyze that one, it requires a larger memory space, right? Now to solve that, in order for us to have a smaller memory space in comparable to static linking, we develop this what we call dynamic linking. So dynamic linking, on the other hand, uses this what we call stub and include the stub for each in the image for each library routine reference. So what is this stub? A stub is a small piece of code. A stub is a small piece of code used to locate the appropriate memory resident library routine. The stub replaces itself with an address during the compilation, during the processing. The stub replaces itself with an address of the routine and executes the routine. So meaning to say, the stub will be converted into an address of the routine. Now what if the address of the routine is not located in the memory, in the main memory? Now if it is not located in the main memory, it will be added to the address space. So take note, since it requires time, so take note, since it will be added to the address space, chances are it requires time for your system to look into those libraries for it to be added in the address space. So case-to-case basis. In the static linking, it requires a larger memory. But in the dynamic linking, it has a smaller memory compared with the static linking, but it requires time in order to load. If your address of the routine is not located in memory, so it requires time for it to be loaded in the address space. But still, there are pros and cons in using those dynamic and static linking. Now another thing, in the dynamic linking, it uses this what we call shared library. So the shared library, the advantage of using shared library is that if you're going to update those library, eventually the dynamic linking automatically uses those libraries since it uses a dynamic approach. While in the static linking, it requires you to recompile again the program in order for it to grab another update another updated copy of those libraries. So we need to think for those the differences between dynamic and static linking. Okay, so prior to the discussion, so after we discuss on the linking, we will proceed to swapping. Now, since the primary concern of this discussion is on how we are going to manage memory in terms of number one, the speed, number two, prevention of the collision, then the number three means of discussing or having or discussing this topic is that for us to be able to know how the operating system manage in order to maximize or to optimize the time of execution. Now, I am talking to time execution because if there were residing a process in the main memory which is idle, so meaning to say you are using you are using the main memory for an idle program, or else if you are using a program a process in the main memory which is not priority at all, so meaning to say you are wasting the memory space in the main memory. Now, to solve that problem, this is now what we call swapping. So swapping occurs when a certain process in the main memory has a least priority, and here comes now the process in the backing store which is in higher priority. Chances are the lower priority process will be swapped in with the higher priority process. Now, the problem in here is that there were some one problem in here is that the time of swapping, because of course since we are so too particular on the manipulation or the time consumed or the manipulation of this memory in regards to the time. So therefore, another problem that may rise in the swapping is that the total context switch time that the process requires. So if the next process to be put in the CPU is not in the memory, it needs to be swapped out a process and swapped in a target process. So a context switch time can be very high. Now, for us to be able to understand what is a context switch time, assuming that I have a 100 MB process swapped into a hard disk with a transfer rate of 500 megabytes per second. Now if we're going to look into what would be the possible context switch time within this certain example, now we are going to divide 100 MB with 500 MB to solve for, or to identify or to solve for the swap out time. So chances are, if we're going to divide 1000 with 500, it will came up with 2 seconds swap time. Now since it requires a swap in and swap out, so 2 times the 2 process, the swap in and the swap out process, so eventually it requires 4 seconds or 400 milliseconds for the entire process to be done. Now, what is the essence of discussing this? So if you have a larger number of process in your backing store, which requires, or which the program thinks requires to be swapped, if that is large enough, so therefore it causes an idle of seconds for it to be swapped in and swapped out. So therefore the time management inside your system is not being optimized at all. So with this, we need to evaluate, the system needs to evaluate the context switch time prior to the execution of the process. Okay, so with the context of swapping, there are also constraints prior to the swapping process. One of the constraint is you cannot swap out an IO, a process with a pending IO. So this is prohibited. Before swapping it a certain process, it will be checked first whether that process contains a pending IO, or there is a pending process on that IO. Okay, so since we're talking on the swapping and since we're talking on process and binding, now in the broader aspect of memory, another thing that we are going to consider is the memory allocation. How does this memory allocation, how does this memory being managed to provide, how does this memory to being managed to optimize its process? Now, talking about allocation, we have two types of allocation. We have the contiguous allocation and the non-contiguous allocation. So, contiguous allocation, a main memory must support both OS and user process, limited resources, and must allocate efficiently. And contiguous allocation is one of the early method wherein the main memory usually divided into partitions. So, first partition is the resident operating system, usually held in a low memory with interrupt vector, and the user process then held in high memory. And third is each process contained a single contiguous section of memory. Now, for you to be able to understand what is this contiguous memory allocation, let's have to have this example. Now, let's try to think that your main memory, the partition of main memory is somewhat like blocks. Try to consider that the partition of your main memory is somewhat like partition the main memory into different blocks. Now, if I'm using, suppose that I have a process, a 10 KB process, which is equivalent to 10 blocks, and then I am requiring, or those processes will be residing in the main memory. So therefore, it requires 10 blocks of memory in the main memory. So that 10 blocks in the main memory is somewhat like contiguous. So they are interrelated with each other. We cannot separate all of those. It is a contagious. It requires a contagious aspect. So that memory is somewhat like, it is what we call a contiguous memory allocation. Now, what is this non-contiguous? The contiguous memory allocation registers used to protect user process from each other and from changing operating system code and data. So base registers contains value of smallest physical address. We have discussed this one already in the previous slides. Limit registers contains a range of logical addresses. Each logical address must be less than the limit address, and then of course the MMU maps this logical address dynamically in order to produce a physical address. So can then allows, so it can then allows an action such as kernel code being transient and kernel code changing size. Now, how does this contiguous allocation being checked? So as we know that the CPU produces a logical address, and then the limit registers will be checked if the limit registers is less than the limit produced by the CPU. If it is less than, they will proceed. So it will be added with the relocation address, and then this relocation address will be mapped into the memory. So this is the continuous. This is the real case, the real scenario, and how are we going to put down those contiguous allocation inside the memory. But take note, the idea of contiguous memory allocation is that it's somewhat like putting a block of memory, or a certain process which is divided into blocks into a memory which is also divided into blocks. So we cannot separate all of those. We cannot put the half of that process into another side of the memory, because it is contiguous at all. Okay. So let's proceed to multiple partition allocation. So multiple partition allocation, it has degree of multi-programming limited by numbers of partition. So variable partition size for efficiency, so size to a given process needs. So holes or block of variable memories, holes of various size are scattered throughout the memory. So since there are various of processes residing in the memory, and take note that those memory requires a specific length, but eventually it only has minimum length, chances are it produces a waste memory, and those waste memory can be considered as a hole. So since assuming that we have 20 processes residing in the memory, and each process produces, some of the processes produces a hole, so those holes are considered as non-contiguous memory allocation. So when a process arrives, it allocates memory from a hole large enough to accommodate it. Now take note that as what I have mentioned a while ago, that when a process arrives prior to its execution, it will require a larger memory requirement. So assuming that I need a 10 KB memory, so for me to be able to reside in the main memory or the RAM, Of course, I need a main memory larger than my memory allocation larger than my required memory. So if I'm going to reside in the RAM, chances are there is a what we call a waste of memory, and this waste of memory is considered as a hole. So process exiting freeze. So the process exiting freeze its partition, adjacent freeze partition, and combine. So the operating system maintains information about the allocated partition. So it is the function of the operating system to identify the allocated partition, which partition is this process resides, and the free partition at all. Okay, so dynamic storage allocation. So there is a problem in the dynamic storage allocation. Why? Because if all of the processes residing in the main memory produces this what we call a hole. Now the problem now is, how does the process, or how does the incoming process looks for a possible memory wherein this process can reside in, or this process will be put it in. So there were possible in on those. I am referring to possible holes. I am referring to the possible holes. Now there are 3 ways on how we're going to look into the possible allocated holes or allocated memories in the main memory or the RAM. So first is the first fit, which allocate the first hole that is big enough. So along the lines of free memories in the RAM, the first big hole which is big enough in compare with your required memory will be allocated for that process. So that is what we call first fit. Now another thing is the best fit. So allocate the smallest hole that is big enough. So take note, it allocates the smallest hole that is big enough. So therefore, among the holes available in the RAM, the system or the system requires to search for the possible smallest hole which is big enough for the process or for the incoming process to fit in. So therefore, it requires time. Next is the worst fit dynamic storage allocation. So the worst fit allocates the largest hole. So the same with the best fit. Unlike with the best fit, the best fit looks for the smallest hole, but the worst fit requires a largest hole for the incoming process to fit in. Now, technically, first fit and the best fit is better than worst fit in terms of speed and storage utilization. Why? Because of course, maybe the best fit and the worst fit in terms of speed is quite comparable, but in terms of storage, eventually best fit is more better than worst fit because it can manage the storage capability wisely in compare with the worst fit.